Okay, so for this Woodward problem, so it's really about being confident with partial sums. So I'm writing out these individual partial sums here. For instance, S3 would be the sum of the first three terms. That's exactly what a partial sum is. S of 5 would be the sum of the first 5 terms. Now, they're giving you a formula for the nth partial sum. So for this particular series, if you want S4, which would mean summing up the first 4 terms, you'd plug 4 in for n, you get 7 minus 8 over 4 squared, or 7 minus a half. So if you use the formula to get this, then you'd be 7 minus a half. Is that 6.5? But we can never lose sight. I mean, the more important thing about S is that you're imagining this. When you think of S4, you're imagining that. That's the sum of the first 4 terms. Okay? So if you want to get, say, it's asking for A3, how can we get A3? So looking at what these are, what could help us get A3? Well, S3 would be these 3 summed up, and S2 is these 2 summed up. So how can that help us get A3? Subtract, right? If you took S3 minus S2, that would be A3, just by thinking about what those things mean, right? What those mean. If you took S3, the sum of the first 3 terms, and subtracted the sum of the first 2, that would be the third term. So then we could use the formula to do that, right? So S3 would be 7 minus 8 over 9, and then we could subtract 7 minus 8 over 4. Whenever that number comes out to be, that has to be the third term of the sequence. So we can use that same thing to find a general formula for an. So how do we get S3? We took S3 minus S2, and that gave us A3. So how would we get an? So we imagine what's the nth partial sum. Would be A1 plus A2 plus all the way up to an, and that's what we're after, right? We're after that. So it'd be nice if we were be able to subtract all those. Sn minus 1. Sn minus 1 will be all those. And so if we take Sn minus Sn minus 1, we get an. So what is Sn? Well, Sn is this. And what is Sn minus 1? Replace the n with n minus 1. So it'll be 7 minus 8 over n minus 1 squared. So what I'm putting in red would be a formula for a sub n, because it's the sum of the first n terms minus the sum of the first n minus 1 terms, leaving the nth term. So what I just put in red would be your answer for part C. Does it make sense? And then the sum, how do we find the sum of a series? So really important concept here. The sum of the series is always equal to what? Yes, sir? Right, so this was the whole big idea of the sequence of partial sums. If you take the sequence of partial sums out to its extreme, you're just basically getting indistinguishable from the whole sum, right? If you keep taking more and more terms of the sequence of partial sums, you're getting closer and closer and closer to what that sum is, because you keep adding one more, right? So imagine the sum of the first 1,000,000 terms, the sum of the first 1,000,000,000 terms. If you keep doing that, then eventually your sequence of partial sums is approaching this. So we're just going to take the limit of that as n gets really big. And what is it? 7. So the series then will sum up to 7, because as n gets really big, this sequence of partial sums will approach 7. Okay, questions on this example? Any questions? But again, it all goes back to your image of when they told you, when they said this sequence of partial sums is this, that you immediately start thinking this. Oh, that's what those things are. S1 is the first term. S2 is the sum of the first two. S3 is the sum of the first three, etc. So that this has to be solid in the background of your thinking as you're working through those problems. Yeah, question.
The definition of SN, is that essentially general term?
So that's our notation for the sequence of partial sums.
Okay.
Yeah, that's the nth. That's the nth partial sum.
Okay.
That's yeah. That was in the book and in class. We used that notation. So yeah. So it didn't say that, but that is consistent with the notation in the book and what we did in class. And then if you're not sure, just email me. Yeah. Yeah. Yes, you.
Sorry,
Yeah. Mm-hmm.
How is it approaching 7 if you are subtracting 7 as well?
No. I'm sorry. In the red is the an term, but I'm just making a mess now. But Sn is only this.
Oh, okay.
So I subtracted this thing myself. So yeah, you're right. But this is Sn. Okay. Other questions? Yes, please.
How do you do part 2 for A?
I'm sorry?
How do you do part 2 for A?
This one?
This
All right, so this would be, if we had n equals 1 to 16, that'd be s of 16, right? So then what do we want? We want to start at 4. That means we don't want the first 3 terms. So we're going to take s of 16 and subtract s of 3, which would be the first 3 terms. See that? Yeah, so this would be s of 16.
Because I was doing S of 4.
Okay, you want s of 3 because you want to hold on to the 4th term. If you do s of 4, it'll start at 5, go 5 to 16. Yeah. Other questions? Okay, next one. Okay, this was kind of an unfair question. I'll give everyone a point back. Don't worry about this if you were confused. But because the problem with this is the limit of this sequence is 0. All right, so when I glanced at it and assigned it, I was thinking it was something more like this. And that you can do. Because what's the limit of that sequence? Just the sequence. ln of 2n over n plus 5, the limit of that sequence would be? ln of 2, right? ln of 2, and then the series would have to diverge, right? If the limit of the sequence is not 0, this is like the big thing from last class. The limit of the sequence is not 0, game over. The series is can't converge, right? What about if the limit of the sequence is 0? Then what about the series? Maybe. Now we have a chance. You're telling me there's a chance, right? Okay, so if the sequence goes to 0, then it may or may not, the series, the sum, may or may not converge. If the sequence does not go to 0, you're done thinking or looking at it. It just diverges. So, but again, don't worry about this problem. I'll give you a point back. So how about this one, last one? All we have to ask is, does it converge or not? Does the series converge? Does the series converge? Yes or no? So, always look at the sequence first. What does the sequence do? The sequence gets closer and closer to 9/4. Meaning, yeah, so meaning when we get out to, in this sequence, this list, we essentially have 9/4, comma 9/4, comma 9/4, comma 9/4, or essentially, right, it's indistinguishable from 9/4 over and over and over again in the list. Now we're going to add those all up. What's going to happen? It's going to keep increasing by 9/4 every time we add. So this can't converge, right? This is divergent by the divergence test, right? Okay, so let's just do a little warm up here. So, quick, we don't take a lot of time, but I want to know for these 4 things, essentially, when you see each of these, you think what? Okay? When you see each of these, you think what? Mathematically. So, for example, if you see x plus 1 quantity cubed, you might think, oh, that's x cubed plus 3x squared plus 3x plus 1. Right? What does this mean mathematically? It means the sum of these four monomials. So, when you see this, you think what? 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 Notice, no chevrons around this. Okay? Without just this thing right here. Mathematically means what? Go. You can discuss. You can think by yourself or discuss. But let's just keep it to like 2 minutes. But this is important. We got to know what things mean. Have the right image in our mind. If we're going to do this, all this stuff. Go. Okay, let's see how we did. See how we did. How about Miranda? How did the first one go?
I'm sorry. So it's not asking us to sum anything, but that value is basically just going to be like 4 times n minus 1 and 4 n minus 2, whatever that n value is. Like if n was 3, then it would be 12 factorial.
All right, so you said 4n times for quantity n minus 1? So how does it work? So whatever this is the first number, right? And we're going to multiply by 1 less than that, right? So it would be 4n just minus 1. And then? Yeah. So you don't want to set off those quantities because 4n is just, you think of it as the highest value, and then you're going to go down by 1 each time from 4n. And then when do I stop? And factorial always stops at 1. So that we're always going to go down to 1. No matter what factorial we're doing, it always goes down to 1. Okay, the next one. What does it mean? Nick, did you get this one? Army Nick.
So this one, I had 2 7s plus 4 13s plus 6 19s. And then drop that to
How many things do I add up?
until infinity.
Just keep going, right? Just keep going. Yep. Correct, right? When you see that, you should be thinking this. When you see that thing with the ugly, the scary summation sign, it's let I be 1, then let I be 2, and then let I be 3, and then we're going to add up those terms, right? We're going to add up the terms of the sequence. Okay, next one. How about this, Nick?
We decided that's just given an input, just a constant. There's no adding or series.
Okay, there's no adding, there's no series, but what does this denote mathematically? What does it mean mathematically? Like what operation, what's going on there?
There's an exponential function there.
Okay, so what does it mean? Micah?
My thoughts were along the same line.
What does negative 3 to the k mean mathematically, Julia?
You multiply k number of negative 3s together.
You multiply k number of negative 3s together. Exactly. It means negative 3 times negative 3 times negative 3, and you keep going. And then somehow you just have to indicate that there's k of them, right? K, negative 3s. That's what that means. It means multiply a bunch of negative 3s together. In this case, how many? K of them. K of them. So if I were to multiply by 2 more negative 3s, then what would this be? Negative 3 to the k plus 2. If I were to multiply by 1 less negative 3, negative 3 to the k minus 1. Okay, last one. Junsi.
2 over 7.
Mm-hmm.
4 over 13.
Mm-hmm.
6 over 19.
Right, it means the list, right? It means the list of values. Same list that we turned into a sum for the second one, right? So this list, does that sequence converge or not? Does it converge? Converges to 0.
Sorry, converges to 1/3.
1/3 as I gets large, right? So then what about this series? Diverges because?
You're just adding closer and closer. You're pretty much adding a third.
Yeah, so if we kept, one thing we could do to keep writing this sum here is we could say like this. It's essentially 1/3, and I'll put in parentheses to mean like indistinguishably close, but not exactly 1/3. So when I gets big, we're just going to keep adding 1/3, right? Or so close to 1/3 we can't tell the difference. And that's going to diverge because you're just going to, every time I increases by 1, your partial sum is going to increase by 1/3. Questions on this warm up here? So when things get more complicated and hard and we're learning all these rules, so we really have to have some of these, the basics have to be down. These can't trip us up, or then we'll never get off the ground. Anybody have a question? Okay, so let's talk about geometric series. We started this last time. The geometric series is of this form. A times r to the j minus 1. And so you see that, last time we said you see that, you think what? See that, think what? What does that mean? Alex, when you see that, you think what? What does that mean?
Kind of like a polynomial added up. So AR squared added to 3.
Commas?
Added up.
Add it up. You got it. So A plus AR plus AR squared plus AR cubed plus AR to the 4th, etc. So this is virtually the same as our geometric sequence. What's the difference? Well, we've got this coefficient, right? A, that's different. And then instead of JR's multiplied together, it's just J minus 1. So it's just kind of like shifted back 1. So there's really no difference than that. Okay? No, saying R to the J and R to the J minus 1 is virtually the same thing. It's just J minus 1 then gives you this R to the 0 term. Okay, so we want to know for what values of R does the geometric series converge? So let's review. What about for a geometric sequence? For what values of R do the geometric sequence converge? Do you remember that? Scott, do you remember?
Wasn't it any R value between 0 and 1?
Between 0 and 1.
Multiply decimal times itself, it's going to get smaller.
That's the right idea, but negative 1 to 1, right? So we said the geometric sequence gets really small, essentially 0, as long as R is between negative 1 and 1. Okay, so now we want to ask, okay, so we've got a geometric sequence, now we're going to add them up. When would that converge, when we added them all up? All right, so we're going to consider the sequence of partial sums. Right, SK, okay? SK is the kth partial sum. And so what would the kth partial sum be? It would be all the way up to A times R to the what? A times R to the K minus 1, right? So it'd be, you'd sum up all the first, whatever, K terms, and the last one would be AR to the K minus 1, because we have that A term to start with. All right, and then what we're going to do is we're going to take that same thing and we're going to multiply by R. We're going to take R times SK, R times the kth partial sum. You say, why do we do that? I say, because it works. Okay, because it works. So we're going to do that. So when we do that, we just have all the terms now multiplied by R. And then I'm going to just position them over so they line up with the ones from the previous one. See that? So you're just multiplying every term by R, and I'm just going to then just move them so they're lined up vertically with the ones. Oh, that should be minus 1 there. That should be minus 1. Okay, and then what we're going to do is, we've got them all lined up, we're going to subtract. We're going to take the top equation minus the bottom equation. So on the left, we'll have S of k minus r times S of k. And what will we have on the right when we subtract? We'll have a minus ar to the k. All these will go away, right? All these ones that were lined up will go away. And we'll just have a minus ar to the k. Okay, now I'm going to factor out the kth partial sum. And that leaves 1 minus r equals a minus ar to the k. And now I'm going to divide by 1 minus r. Nothing hard yet, right? Okay, and then I'm going to split that up. I got two terms in the numerator, so I'm going to split it up into a over 1 minus r minus ar to the k over 1 minus r. Still nothing hard, right? Now, I've got a formula for the kth partial sum. How does that relate to the actual sum of the whole geometric series? So how can I relate the sum of the whole series to the kth partial sum? Right. So if we take, like, let k get really, really big, and then you just let it get bigger and bigger and bigger, you just keep adding more and more terms, and it approaches the whole sum, right? That's what we said. The limit of the partial sums is the whole sum, the whole series, right? So the sum of the series is the limit of the sequence of partial sums. We know that from before. So I'm going to evaluate this last expression that we got as k approaches infinity. And we need it to converge, right? So looking at the second part, so this first thing has nothing to do with k. It doesn't care what k does. It doesn't care how big k gets. It's just a over 1 minus r. Now this thing, when will this converge? It's a r to the k. So this is a sequence of a r to the k over 1 minus r. When will it converge? What kind of sequence is that? R to the k. That's our geometric series, right? R to the I, we called it R to the I up here, but it's R to the k. When's that going to converge? Between -1 and 1, right? So we're just going to apply what we know about geometric sequences right there. That will go to 0 if R is in our range here, -1 to 1. Leaving what? Leaving a over 1 minus r. Now that's only true if r is between -1 and 1. So, for what values of r does the geometric series converge? It's the same thing as the sequence, right? It's the same conclusion as the sequence. If the sequence converges, if r is between -1 and 1, then the series will converge too. Okay? But even better than that, we know what the sum will be, right? We know exactly what the sum will be. What will the sum be? A over 1 minus r. The sum will be a over 1 minus r. So in showing for what values of r the geometric series converges, we got the bonus of this is what it converges to. Okay, any questions on that little derivation? There's nothing in there that's hard. I mean, there's a lot of things that we did, but not one of those steps is really too bad. They all should make sense. Okay. So now we finally made it back to the turtle. So maybe the turtle. He walks half the yard the first day, a quarter of the yard on the second day, an eighth of the yard on the third day. So what I want you to do is express that as a series. Express that sequence as a series. Okay? And so, and I want sigma of the general term of the sequence, right? I want sigma notation. So what would sigma notation be to express this thing as a series?
1/2 to the I.
He wants 1/2 to the I. Seth likes it. 1/2 to, or you also say 1/2 to the I. Is that agreement? Yep. That's what it is. So, yeah, so, and I actually like that better. 1/2 to the, I'm using J this time. So we want to be able to use whatever index they throw at us. Here I'm using J. Okay, so is it a geometric series? Yeah, we keep multiplying by the same number to get the next term, right? We keep multiplying by 1/2 each time. Is it in the form that we have there? Not quite, right? It's close, but what we really need is we're starting at the right index, we're starting at 1, but we need something times something to the j minus 1. So we need to change it up here. We need to change 1/2 to the j is the same as what times what to the j minus 1. So first of all, what will be to the j minus 1? So yeah, we're still multiplying 1/2s together, okay? So the question is, what do we need to multiply j minus 1 1/2s to get j 1/2s? Right? How does this many number of 1/2s multiplied together compared to this number of 1/2s multiplied together?
Same.
What do I need? You should see that we need one more 1/2, right? Does it make sense? This goes back to that, what? -3 to the k, right? -3 to the k is k number of -3s multiplied together. So here, if we want to get it to look like this, by changing it to 1/2 to j minus 1, I have one less 1/2 than I did before, multiplied. So now I need to show it out here. So that means a is what and r is what? A is, Alec? And r is? They're both 1/2, right? Is this a convergent geometric series? Is this convergent, and how do you know? Is this series going to converge?
Yes.
Because
It's the rule that R is between.
r is between -1 and 1. Check. So we know this is going to converge. And what's it going to converge to? A over, we just derived it, a over 1 minus r. So it's going to be 1/2 over 1 minus 1/2, which equals 1/2 over 1/2 equals 1. And what does that sum mean? It means the sum of all the distances that the turtle walks, right? The sum of all the distances the turtle walks. So, does he make it across? Yeah, he's going to walk exactly 1 full yard length. But he can't ever stop. If he ever stops, he doesn't make it. He's got to keep going, right? Why? Because you have to add all infinitely many terms together. If you take any partial sum, he's not going to make it across the yard. But if you take the whole series, he makes it. All infinitely many terms. Does it make sense? So you can't think in terms of individual partial sums, because if you do, then you say he'll never make it. You go 1,000,000 days, he won't make it. You're right. He goes 1,000,000,000,000 days, he won't make it. You're right. But if he goes all the days, which is all infinitely many days, then he makes it. Okay. So he makes it, but we'll never get to see it, right? We'll never get to see that. Okay, another example. Try this. So here is, this is an example, and so we see that we get the hint that it's geometric because we have numbers to the powers of I, right? That's the whole idea of that your index is your power. Your index is your power. That's the clue that it's geometric, and that's what we have here. But we got some mess to clean up here. Again, what we need in the end is we need something times something to the j minus 1. Or I. I'm using I now. So what's the something to the I minus 1 going to be? Can you see? Negative 3/4, right? Negative 3/4. So we know in the end we're going to have negative 3/4. Okay, so in the top we had I plus 2 negative 3's, and we just grabbed I minus 1 of them. Do you see that? So we just grabbed I minus 1 of the negative 3's, but really it needs to be this many, I plus 2 negative 3's. So how many negative 3's did we essentially take out to get I minus 1? 3. So we're going to have negative 3 cubed. Does everyone see that? Now when I have negative 3 negative 3's, and I minus 1 negative 3's, that all makes I plus 2 negative 3's. Did you catch it? Does it make sense? Okay, what about 4's? Uh-oh. Right? So I have I minus 2, and I just kind of created an extra one, right? So yeah, so if you want to keep it in the denominator, what would I need to do in the denominator here so that in the end I have I minus 2 fourths? Divide by 4, right? I need to divide by 1/4. Just looking across the denominator there, I had I minus 1. If I take 1 away, divide by 4, then I have I minus 2 fourths. And then I still have the 5. And this dividing by 4, some of you noticed that would be the same as multiplying by 4 up here. So my A value is 4 times negative 3 cubed over 5. And my R is negative 3/4. Is it going to converge?
Yes.
And I'll let you do the rest. So yes, it converges because my R is in the right range. And what does it converge to? Whatever you get when you do A over 1 minus R. So the sum is A over 1 minus R. So we won't take the time to do it. But does that conversion make sense? Did I lose you? Yeah.
I still don't understand how you went to the negative 3 cubed.
Okay. So how many do I have? I have I plus 2 of them. And I'm going to grab I minus 1 of them. So if I had this, let's do negative, so how about this? Negative 3 to the I plus 2 is negative 3 I times negative 3. Would you buy that?
Yeah.
So now I want even one less of these, but I need the product to stay the same. So if I took even one less of these and latched it on with this one, then it'd be I minus 1 of them times 3 of these. Is it better? Yeah. Other questions? Okay. Soon as if you have a geometric series and this thing is out of the range of the negative 1 to 1, you don't have to do any more work. It diverges, right? It diverges. Any more questions about? Yeah.
So why does it divide by 1/4 instead of like negative 3 cubed over 1? Because if you wrote that as a fraction, then it'd be like 1 over 4, and you could multiply 1 by the negative 3 cubed.
So we have one more 4 than what we actually have in the original thing. So we don't multiply. We have to divide 1, right? So when we divide by a 4, then we get 1 less than this, which is the I minus 2. So it wouldn't be 20. It's 5 times a 4th. I think you said 20.
Because if the 1, we have like 1 over 4, wouldn't it just go
This
up?
would be 5/4. Yeah, it could go up here, but it wouldn't be 20. It'd be negative 3 cubed times 4. That's what I did up here. Negative 3 cubed times 4 in the top, divided by 5. Is that? Other questions? Okay. So let's do something called a comparison test, which I didn't. Okay, so one thing at a time here. I guess I didn't set up the. Okay, comparison test. If you have two series with positive terms, and you know one of them is divergent, so we got these two series, AI, sequence BI, and you know that the sequence BI is divergent. And you also know that every term of the sequence AI is greater than or equal to the terms of BI. Then does it make sense that you could say AI is also divergent? It should make sense. So you've got all these sum in BI that sum up to something that's divergent. And then all the terms of AI are greater than or equal to each of their terms of BI, then AI would diverge as well. That's called the comparison test. Okay, now suppose, so given a series AI and you suspect it's convergent, how could you use comparison to prove that the sum of AI is convergent? Can you write a similar statement to that one up there? So you suspect that the sum of AIs is convergent. How could you prove it with comparison? So what would that statement, can you rewrite that statement up there that would be proving that the sum of the sequence A is convergent? Give it a shot. What would it mean to prove by comparison that it's convergent? So if you need to work with someone else, work with someone else. But we're going to try to write that ourselves, right? So you're going to write something similar to this that would use comparison to prove that a series converges. What do we think? Tell me, in the white t-shirt, tell me your name again. Yeah, no, white t-shirt. Yep. The one in front, not wearing the gray. Okay. So what, did you get it? Tell me your name again. Connor. So the one we're comparing it to has to be what? I'm sorry. So the series that we're comparing it to, should it be divergent or convergent? Yeah, it should converge. Okay, and then also? Right, so the BI, all the BIs need to be now greater than the R's. So R's need to be all less than or equal to. And then we could say that the one we're testing, right? So if we have it, so the one we know, let's think of the sequence of partial sums, is leveling off like that, then R's would have to be less than that, right? R's, in order to say definitively that the one we're testing is convergent, all those, if all the terms are less than or equal to the terms of the BIs, then it would have to converge also, right? Because it would have to level off somewhere below where the one we know levels off. What if you have a convergent, a series that converges, and all yours are greater than or equal to the terms of that one?
Whether it diverges.
You can't. The jury's out, right? You can't say anything. It's either gonna. It could converge, or it could diverge. Right. And the same with the opposite. All right. So.
So like the same would be true if like one was divergent. It's like all the terms of the other terms of less than
Right.
this,
Exactly. Yeah. If you have one that you know diverges, and then when you're testing, all the terms are less than or equal to that, what can you conclude? You can't conclude anything, right? All right. So let's look at these then. What about this first one? 1 over I cubed plus I plus 2. What do we think about that? Do you think that converges or diverges? And why? Converges because? 1 over I cubed plus I plus 2 compares to what? What would we compare it to?
1 over I cubed.
1 over I cubed. And what do we know about 1 over I cubed? The sum of 1 over I cubed. Converges by? P, that's a P series. P greater than 1, right? P equals 3 greater than 1. 1 over I cubed, that series converges, so this one will converge because all the terms are less. By adding in the denominator, you're getting all terms that are less. Okay, what about this next one? 3 over radical I minus 2 cube root of I. First of all, do you suspect that it's convergent or divergent? I heard convergent. Convergent. People are saying convergent. And what do you want to compare this to show that it's convergent? All right, so let's do 3 over square root of I. That's no problem. 3 over the square root of I, which the series converges, right? Ooh. Why doesn't that converge? This is another P series, but P now is less than 1. P is half. So this is divergent.
Doesn't slow down.
But how does ours compare to this? We're subtracting a positive value in the denominator. So we're making the denominator smaller, making the whole thing bigger. So actually, I'll put it over here. So the one we have, minus 2 cube root of I, is how compared to what we were just looking at? It's actually bigger than that. And we know, what about this series? It diverges. The one we have is larger than a divergent series, so it diverges. Okay, last one. Don't have time. That's a good one for recitation, if you want to do that one in recitation today. Okay, we finally got to the turtle, but we're still moving like a turtle.